And now we're actually going to get into some calculations. Use the bond dissociation energy tables on the conversion and equation sheets to determine which of the following releases the most energy. Now, we're going to do some bond dissociation energy calculations now. And so it's worth mentioning that releasing energy occurs when a bond is made. And if you go all the way back to the beginning of this lecture outline, when we looked at pictures of a bond forming, we said that if you take two atoms that are very far apart, they will have no attraction, and that when you bring them together, and these are just forming a covalent bond, by the way. Not an ionic bond, so these are going to form something like that. Their attraction, or the bond, is when they've gotten close enough to maximize their attraction. And it's an attraction, so think of them as lowering their potential energy of position, and that it means that they're going to release energy to the surroundings. So, and here's the take-home message. Releasing energy occurs when a bond is made. It takes energy to break a bond. So, it takes energy, or it requires energy to break a bond. And then if we go to our conversion and equation sheet, there we go. On the conversion and equation sheet are the average single bond dissociation energies for a whole host of single bonds. And what you want to do here is, looking at these four choices, this is a multiple choice question. First off, we're going to be making a bond because the question says releases energy. So we're going to be forming bonds. And then you just want to go to the list and see which one has the largest number. I will say this, the single bond dissociation energy table, these are all positive numbers. That's why they're called bond dissociation energies. So that means breaking bonds. This is the amount of energy it takes to break 1 mole of bonds. For example, to break a hydrogen iodine bond, 1 mole of them, it takes 299 kilojoules of energy. If you want to break 1 mole of hydrogen-hydrogen bonds, it will take 436 kilojoules per mole of energy. Okay? And then, so these are the single bonds up here in a nice well-organized table. Here are single, double, and some triple bonds. And what you can see is that as you go from single to double to triple, the same bond becomes stronger and holds more energy inside it. And so it takes, or it requires, right? It takes energy or requires energy to break a bond. It takes 813 kilojoules per mole to break a carbon-carbon triple bond. Or if a carbon-carbon triple bond is made, it releases 813 kilojoules per mole of energy. So that's how you use these tables. My choices, also we're not breaking any bonds because breaking bonds requires energy. So now I'm going to go for silicon, sulfur. Silicon, sulfur is 226. Kilojoules per mole, and I'm going to write minus next to it because it's releasing energy, and releasing energy is negative. And then let's see, OI. OI is 201. So forming a silicon sulfur bond will release the most energy. Any questions about that?